dear Armin. It is a great pleasure to have been invited to your talk series. So with COVID, we don't manage to do too many travels those days. So in each of my talk, I put a little virtual travel for you. And this is a beautiful picture, a piece of art taken from the beautiful picture of the couple in Milano, which is very famous, which name is Futuro Dinamica. And the concept that I'm going to talk a lot today is this idea of symmetry and symmetry breaking, which is why I chose this picture to present or introduce the concept. So what I would like to do today is to try to carry you through two paradigms of how the brain works through the lens of neuroscience, and trying to reconcile a very powerful concept of information propagations that has been very well defined, we will see, at the microscopic level, especially at the synaptic connectivity, with a very influential history, starting with the discovery of a neuron last century, and continuing with system-level descriptions of what can be best understood as collective behavior or mass action. And so a number of people who are listed here have questioned the problem of information flow in the brain, and especially at rest. The paper that I'm going to present to you in the first part of this talk is this paper here in 2014 in Frontiers in System Neuroscience. It's a very short paper. Some people even said it was a funny paper, and I hope that some of you will take a little peek at it. And to introduce the problem, maybe Shanahan said it best in 2010, so I'm going to take it with him. Most previous synchronization studies or studies of brain collective behavior focus on stability. Yes, yet many complex systems, such as the human brain, do not converge on stable synchronized state, and therefore we need to develop new theories, new concepts, and new methodologies to analyze this problem. So we are going to start with a little overview, very long overview about why the idea of propagation is so influential in the history of neuroscience. And we are going to start with those two. So Golgi, in the late 18th century, invent the black reaction, a dye that you can insert in neurons to be able to prove the theory initially proposed by von Gerlach, that the neural tissue was a continuum, a reticulum, and didn't have independent units. And Ramon y Cajal, of course, support the alternative theory, which he called the neuron doctrine, that they are finite spatial elements, which are the neurons, and they're discontiguous with their neighbors. And of course, Ramon y Cajal, with beautiful anatomical work, will use the black reaction of Golgi to demonstrate the existence of a neuron. And this gave the first influential series of Nobel Prize in 1906, which continue with a work in 1932 by Adrien, who is going to describe the impulse activity within nerve fiber, and Sherrington, who define the coordinative inhibition in neural tissues, and also at the same time coins the word synapses, which is going to give us an articulation of propagation in two manners, in the axon electrically and at the synapse chemically. A little bit later, Lowy is going to decipher what's happening at the synapse with this concept of neurochemical transference, and Dales is able to characterize the secretion of acetylcholine and identification of the precursor of transfer using neurotransmitters. A little bit later, in 1963, we have Eccles, which is going to uncover two mechanisms of excitation and inhibition at the synapse, and Hodgkin and Huxley, we will be impaling squid's giant axon discover the transfer, the ionic mechanisms that propagate the action potential, and they theorize also the existence of ion channel. And a little bit later, in 1970, and I'm going to stop there because there will be much more to say in the wake of these studies, Katz discovered that the release of neurotransmitter in the nerve terminal is quantal. And Van Euler and Axelrod characterize the condition of storage, activation, and deactivations of neurotransmitter in the synaptic terminal, and so on and so forth. So all those aspects of cellular neurophysiology from the past century have given us a very strong and important idea that the brain has information or some events, some energy and some matters that is propagated or that is transferred from one unit to another. And that's a very, very important asset from cellular neurophysiology. Now we are going to change scales. So as you know, people often, from the lens of physics, search very similar phenomenon at the small and at the large scales. But when you change scales, you have to be very careful not to convey or carry over concepts and principles without questioning their validity. And so on the other way around, in the 70s, Walter Freeman and others were the first to elaborate the concept of mass action in the nervous system and the requirement that many units in the complex brain of evolved organisms, including the rabbit, the cat, and the monkey and the humans, needed to recruit not a single neuron to do a single thing, but many neurons to achieve a common goal. And it was very, very well described in this study, this breakthrough study by Gray, Koenig, Engel, and Singer in 1989, which is the recording of the visual cortex of a cat, which was anesthetized, but which receptive fields for two neurons, a neuron which receptive field is here and a neuron which receptive field is here, were stimulated with three kinds of stimuli of varying degree of perceptual coherence. In this condition here, there were two bars moving in opposite directions. In this other condition here, there were two bars moving in similar directions. And in the third condition, there was one single bar which was moving across the visual field simultaneously across both receptive fields. And what they found, and you see it in white here with the autocorrelogram, is that when the two perceptual objects were unrelated or incoherent, there was no structure in the autocorrelogram, demonstrating the lack of periodic coordination between the receptive field, between the activity of the neuron coding here and the neuron coding here. When the two bars were distinct but moving coherently, there was the emergence of a distinct peak at zero lag, near zero lag synchronization, and little satellites here. So the emergence of synchrony is what you are seeing here, which was not obvious in surrogate data. And when the bar was a single bar transecting both receptive fields, what they showed was this huge tendency for coordination near zero lag, and those huge satellites which entail the emergence of synchronization between two neural assemblies. So this result and a few others have triggered a real deluge at the system level, at the mesoscopic and macroscopic level of studies which sole goal was to find neural synchronization in the brain. And they were articulated under the idea that neural coherence was a very useful concept for mass actions and for perceptual binding, and that was the manner through which computations are instantiated in the brain. So for a couple of years, there were raging battles in the editorial back office about this result, because for many, many decades, the emergence of synchronization, especially with the alpha rhythms and with rhythms related to sleep, had been strongly associated with loss of function, loss of consciousness, loss of attention, and things which are deleterious to computation and effectiveness of a cognitive system. And for a couple of years, there was a very strong pushback that this kind of results were an artifact of the anesthetic that has been used to immobilize the cat as their receptive field were carefully monitored, and that it was not reflecting perceptual awareness or perceptual integrations. Until these very beautiful studies in 1997 by Charlie Gray and Diana Di Prisco, which reproduced the Gray study of 1989 using an alert cat. So they did a very beautiful study where they managed to remove the anesthetic and keep the stationarity of the recording elements. And they were allowed to show that neural coherence and synchronization was allowing the cooperation of multiple neural ensembles for computation. And so this gave us at the meso and macro scale the idea that synchronization or tendencies towards synchronization was a functional feature of the brain and maybe intimately linked to computation and was not a bug or an artifact of anesthetic. So what I would like to bring into the picture today, and I think that's the most important thing that I'm trying to accomplish, is to show you the tension and the irreconcilable tension that is between those two concepts, transfer of information and synchronization. And I'm going to take a little cartoon here. I put time on the horizontal axis here and space, let's say 8 functional units, doesn't matter what they are, on the vertical axis. And if you have transfer of information, you might meet something like this. The information is in unit 1, is passed on unit 2, say a neuron or a neural ensemble, and 3 and 4 and 5 and 6 and 7. There's only 7. So we have flows of information, but we have absolutely no mass action in this example. And when the neuron has passed its activity to a neighboring neuron, it has lost the ability to collectively work with a neuron because they don't have synchronicity or coincidence in time. In contrast, the second series of concepts which I introduced to you, synchronization, in their strictest, more rigid form, which is what we are going to question today, do have mass action. Many functional units cooperate to a common goal, but in their strictest form, especially when there is presence of attractor, they cannot be flow of information because the information is in all the system, is ubiquitous and cannot be moved around in a principled manner. So in the second part of this talk, I would like especially to present the result from this paper here. And I would like to introduce a mathematical model of metastability. And I would like to tell you that my definition of metastability will be related to the phenomenology of this model. There are several not completely compatible or not completely incompatible definition of what metastability means. For some, especially in computer science, metastability is the inability of a system to decide between two alternative propositions, which have been illustrated with this thought experiment by a priest in France, which name is Buridan. The donkey does not know if it wants the water or the straw, and is going to stay there and being unable to satiate his physiological need because it hesitates between two different states. In electronics, for instance, metastability has been described as a flip-flopping between two states or a bistability between two states. And people in electronic and strong control system find metastability to be a very undesirable phenomenology of their system that they're trying to prevent. In contrast, I'm going to try to convince you that metastability brings a lot of adaptation for a functioning brain in terms of cognitive flexibility, in terms of mass action and transfer of flow. And I'm going to try to describe the model that we use to try to understand how it works. The model has been defined as a reproduction of phenomenology of both behavior and brain dynamics. So it's a model which is empirically valid, and it has been very, very well studied at my research center in particular for the last 30 years. So this model of coordination is born from these equations here, which we call the extended Haken-Kelso-Buns model of coordination, which is in this paper in 1990. And it is going to articulate collective variables or coordination variables, which I would like to tell you about a little bit. So in dynamical systems, we have the trajectories of a piece. If I take two oscillators here and they oscillate, I can have a state variable for this oscillator, and I can have a second state variable for this other oscillator. And that's what I'm going to call the dynamics. The work of synergetics told us that it was very important to pay attention to something else, because those units are typically reciprocally or unidirectionally or in a complex manner coupled with each other. We are interested in the coordination dynamics. Those are variables that are going to tell us the evolution of the coupling and uncoupling between those two time series. And we call that a coordination dynamics. Those time series here being oscillator, and a lot of my work being about oscillator, we find it extremely straightforward to turn our attention to a variable which is called the relative phase, which is the difference between the phase of this oscillator and the phase of this oscillator over time, which you see represented here in blue. And this coordination dynamics will tell us something about the episode of transient integration of synchronization, which we call dwell, and transient release from synchronization, which we call escape, which we see represented here. So phi is this coordination variable. That's a variable that is very important both in theoretical and in empirical work. For certain parameters that I'm going to show you in a moment, it gives rise to 2 or 1 attractor. And for other parameters, the attractor disappear and only attracting tendencies remain. And this is in those regimes sans attractor that the property of metastability is observed. So here's a picture of this model. The equation is reproduced at the bottom here. So that's the rate of change of this relative phase, how it evolves over time. And it's governed by this equation, which has a term for broken symmetry and 2 terms for coupling. And this term for broken symmetry has something to do with the realism that things that we find in real life in nature, like 2 neurons or body parts, etc., often have different intrinsic frequencies. Let's say that I have a neural ensemble here and another neural ensemble here. They want to work together, but they might have different frequency preference. In a strong mechanical system, say your car or your coffee machines, this lack of complete concordance is often an obstacle for working together, and therefore there cannot be interaction between them. But what we find in complex biological systems is that they find a way to transcend their difference and to work together. And this is a reason why we are very interested in this complex relationship between things which are different. So this parameter here, delta omega, is what I plotted here on this part of the graph here. And the plot, each ribbon is a phase portrait, and it's going to tell us the change of the relative phase, the future, if you wish, as a function of its current state or current properties. So we can look at this graph together, and we can look at the first ribbon, which is in the front of the figure here, if I find my little cursor here. So what you see here is this ribbon as ondulation going up and down the gray plane, which represent the value delta phi over dt. The rate of change of the relative phase is 0. And that is where we find the fixed point. That means whatever the system is now, it will be there forever. Unless noise, unless input, but it will be stuck in there. And this is the gray plan that you see over there. So as you see, when the oscillator, the two oscillators here, are perfectly identical, which is what I'm representing in the front of this figure here, I find a circle here, which I painted black at 0 radiant, and another black dot at pi radiant, and those are attractor, and I see two other dots which I represented as open circle, this one here and this one here, and those are the twins, the evil twins of the attractor, and they are called repellers. And I'm going to show you a little bit how we find them. So let's say that at the current time, my phase between my two oscillators is going to be let's say 2 radiant, something here. So I go here and I find that the rate of change is going to be negative. So if I'm 2 radiant now, in a couple of seconds, or milliseconds, I'm going to be 1.9, 1.8, 1.7. I'm going to move in that direction. And so you see, I put a little arrow here to manifest this. And the flow is going to move toward this black dot here. The same happens here, where my rate of change of the relative phase is negative. I'm going to move into that direction. If my rate of change, let's say 4 radiant over here, my rate of change is positive. So if I'm 4 radiant at the current time, I'm going to move in that direction, 5, 6, etc. And I'm in the wrong place, but let's say I'm at 2 here, and I'm going to move toward the attractor at pi here. So you see that the points where the 2 arrows point toward as those I call the attractors. And if there would not be change in the system, if there would not be perturbation or noise, the system would stay there forever. And you see that the repeller have this property that the least nudge or the least anomaly due to noise will kick them away, and they would go over there. And those are called the repellers. So when I have a system of 2 oscillators, which is perfectly symmetrical, what I find is a tendency for integration at in phase. Both oscillators go up and down at the same time. And at pi radiant, which is also called anti-phase, one oscillator goes up while the other goes down. And this bistability is found prominently in many physical systems. When I break the symmetry, moving away to ribbons further in that direction, what I'm going to find is that the attractors move slightly away from strict in-phase and anti-phase. So they move a little bit to the right here, until eventually one of them disappears and the second disappears as well. When the first disappeared, we went from a regime which is bistable to a regime here, which is monostable. And when the second disappears, we go to another regime, which is called metastability. So in the reach of this surface, we have tendencies for integrations, which we call dwells. And in the top sections of those ribbons, you have tendency for escape. The 2 oscillators are trying to deal with their natural difference and are trying to catch up on you go too slow for me, you go too fast for me, we are going to catch up on what we really wanted to do all this time. So, oh, we went to the wrong place. So there are two properties in those theoretical models that generate metastability. One is this delta omega term, the difference in intrinsic property of the two oscillators. So the fact that one neuron likes to oscillate at 7 Hz and another neuron likes to oscillate at 8 Hz set them up to be able to express metastability. And the second are those two parameters here in the coordination equations, which are the coupling strength, with the fact that when the coupling is strong, you have state of synchrony. When the coupling is weak, you lose those states of synchrony and you develop this metastability property. Many other people have studied the origin of metastability in a variety of models related to the one I showed you or different one. And they found that beside broken symmetry in intrinsic frequency and weak coupling, some other aspects of neural organization or oscillator organization that generate metastability are sparse and asymmetrical coupling, so structural asymmetries in the coupling, and weakness in the quantity of link to a functional unit, delays, as well as noise. Noise is not necessary in the model I just showed you to generate metastability, but when metastability is there, it helps precipitate the switch between functional states. In a model which has been evolved from those pairs of two oscillators and try to explain what happens when you put into view a full spatiotemporal generalization, we turn our attention to a model of Kuramoto and Batoktok in 2002, and we reanalyze the phenomenology. Kuramoto and Batoktok were very surprised in a model of a ring of oscillator to find that with certain conditions, they found what they described as the existence of a group of oscillators which was stably, coherently organized in their dynamics that you see here in green, and another which they called incoherent. And this coexistence of coherence and incoherence was extremely puzzling from the standpoint of this model of coupled oscillator, and they call that a chimera state. And this chimera state, when we reanalyzed it, we found that it had the hallmark that I already introduced to you, which is namely that the oscillator dwells together. So whenever here, this is just the phase, not the relative phase of a bunch of 128 oscillator. When the lines are parallel for a brief period of time, that means that they are phase locked or that they tend toward integrative tendencies. So you see that there are periods of time here where a lot of the oscillators come together into mass actions. And you have other period of time here where those are working together, but those do not. And you see that the dual are long for some units, shorter for some unit, even shorter for over and for over and over, creating this kind of intricate spatiotemporal metastability where coalition or information constrict and expands, and in more complex attractor form may also move in the systems. And so we rewrote this system as when the coupling is orderly, when the coupling strength is strong, and when the components are very symmetrical. In the back here, we have stability in all those corners. There's a fringe here where we have this hybrid system of stable and metastable, which is shown in orange here. And there's a core, a huge core, where all the units are spatiotemporally metastable. So now I'm going to take a few minutes to move you through definitions. By now you have probably understood that I'm not too fond of attractors, at least in the coordination dynamics, because there might be multiple levels of descriptions. The metastable regime might itself be an attractor, but attractor in the coordination dynamics makes for a brain which is in jail, which cannot move through its state unless energy comes from the outside, like a stimulus, an input, or whether there's a form of noise that coalesces from the body to switch it. So this brain could not have this endogenous dream or open thoughts at rest, because it would be entirely driven by the external input or by the noise. And this is one of the arguments that we have to say that attractors are not desirable in the brain. Metastability is a regime of coordination without attractors in its order parameters. A chimera is a regime of coordination which has one part attractor and one part metastability. Those bitables tendencies, which are very well reflected in a lot of physical and biological systems, organize the coordination with two characteristic regions, near or at in phase and anti-phase, which is a very important principle. And I would like to tell you more about the change in the system. When we have a state of synchronization, when we have attractor, we have two ways to change from state to state. One is a bifurcation that would require something coming from outside, an external variable, that change the structure of attractor, like in the ribbon figure I showed you, to move from one ribbon to another one. And this would generate a change in the coordinative state or in the coordinative tendencies. There's a different concept which is called a transition. When you have a bifurcation, you have a transition, but you can have transitions without bifurcation. And this is for all the systems which have bistable states or bistable tendencies. If there is noise or if there is emergence of spatial scales, you can have change from one regime to the other. And finally, a non-equilibrium system is a system that continuously changes its states or tendencies due to either external input or intrinsic complexities. So those are definitions I thought that some of you might like to review a little bit. And now I would like quickly to show you what we are going to look for in empirical data. And especially I'm going to show you the bivariate view when I have two, say, neural ensemble. Here, for instance, I show you this neural ensemble. It's an oscillation which we found a couple of years ago, which is called phi complex. And here it's another oscillation, which is called a mu. And those two in color brown from the vertex and color red from the centroparietal regions here, you can catch them briefly in dwell and escape dynamics. And this is one of the things we are trying to find and recognize in the data. We can look at the relative phase, and we want to see that it dwells and escapes. And we can look at the frequency distribution, and we should find that those two oscillators reflect the broken symmetry of their intrinsic disposition and have a little bit of separation, not have the same frequency, which you see here. In the spatiotemporal view that we talked about a little bit earlier, for instance, the chimera of the spatiotemporal metastability, we should see those oscillations at a broad range of frequencies, as you can see here. And we could see also dwell and escape across those multiple frequencies with a model that resembles this Kuramoto and Bak-Tok-Tok model here. So now we are ready to look at empirical evidence. And the first episode of coordination in the brain where I was absolutely sure that I was dealing with real and not spurious tendency for collective actions was this little episode that you see here. If you have normal color vision, you see three ensembles in blue, in magenta, and in green here. And you see that we have a little bit of phase delay between them. And this reflects the broken symmetry we were talking about. And for a brief period of time, the delay between them is going to stabilize. So blue, a couple of milliseconds later, magenta, and then green, blue, magenta, green, blue, magenta, and green. And then suddenly this order disbands, and you see the delay between the three phase aggregate has changed tremendously. And this tells us that this transient dwell or tendency for synchronization has terminated. This example is chosen carefully because of the time delay or the broken symmetry. It cannot be explained by spurious synchrony that results from the volume conduction in the brain, the ubiquity of the electrical field. So we know that we are dealing here with a transient synchrony of the brain or a transient tendency for integration of a metastable dwell. We don't know which one at the moment. And we find that those episodes are extremely brief. We are here in the 10 Hertz, and this episode lasts 170 milliseconds. So we found that the brain was a succession of those temporary states, and that they were brief and spatially discrete, spatially sparse, and not amplitude modulated, as had been found, believed before. Here's another example. Here I sample two oscillations from the left and right Rolandic regions in green and in orange, which are the mu rhythm, also in the 10 Hertz range. And those are two sensory motor cortices, which have a lot of business to work together during bimanual coordination, the coupling of sensory motor functions. And when I look at the relative phase, I find that sometimes there's only one of them which is present. Sometimes both of them are there, but they are not locked. They might synchronize briefly, anti-phase or in phase. And so they have this rich dynamics where they play together sometimes and they play independently at other time, which you see reflected in this power spectrum here, where you see that the green mu, which is in the left hemisphere, in that particular subject, has a few fractions of an Hertz slower intrinsic frequency or coupled frequency than the right, which is here, which is again the broken symmetry in intrinsic dispositions. So I remind you once more that metastability reflects this symmetry breaking. And now the last thing I would like to show you in terms of empirical data is the relationship between spatial scales and the spatial level of analysis and metastability. So I remind you that electrophysiologically we've developed methods at the micro scale, like single unit recording or reconstructed single unit from multi-unit, the local field potential, and some macro level recording, like the surface recording that we might do. And I would like to remind you the principle of phase coherency in physical system. But you know, if you have a noise cancelling headphones with you, which is that when two waves are perfectly aligned, their amplitude is consolidated and they can continue to exist at a higher level of description in that direction here. When the phases are decohered or misaligned, which can be the effect of broken symmetry or can be the effect of independence, then they don't transfer to the next level. So that means that at the micro scale, for local ensemble, only the most aligned of the dynamics is transferred to the mesoscale, and only the most aligned dynamic of the mesoscale is transferred to the macro scale. And with this in mind, that's going to tell us that at multiple spatial level, we have different phenomenologies. And if I take, for instance, this scalp pattern that is experimentally observed with EEG, with surface electrode, where I see two ensembles for a period of time, 1 and 2 is difficult to see, which involve neural ensemble having maximum signal at this electrode and that electrode, and another one here, which has maximum signal in that electrode and that electrode. And you see that for 1 to 2 cycles, this transient spatial temporal pattern exists, then it vanishes, and a new spatial temporal pattern exists. For a lot of time, we question whether this dynamic reflects state transition, a bifurcation or a bistability in the brain. But we later try to do a thought experiment that tells us that perhaps it's because the system at rest is continuously across scale in this regime of spatiotemporal metastability. So let's imagine that the neural population, which is responsible for this signal here, is coincident and then scattered, phase scattered for a period of time. And the same happened here. And then for this population, it's first scattered and then coherent, and again here. Then at the mesoscale, we would only transfer the signal from the first part of the signal, here and here. And that would give rise to this temporary patterns. And then from the second part of the signal, this and this would give rise to a collective signal at the mesoscale. And then I would be able to pick it up here at the macro scale at a second period of time. So what I'm trying to do here is that metastability, being a stationary tension regime, creates those patterns, those spatiotemporal patterns that resemble state transition, but that need not to be state transition. So metastability has been shown in the last 20 years in a lot of systems at rest, during REM sleep, in culture, hippocampal networks, under conditions manipulating working memory. It has been speculated, obviously, very strongly as a basis for consciousness and during cognition and behavior. And it has been shown to be affected by cognitive flexibility or its deficit during traumatic brain injury, emotion, psychoactive substance, altered state of consciousness, deep brain stimulation in Parkinson's disease, cognitive traits that are characteristic of autism, Alzheimer's disease, epilepsy, as well as stroke. And I need to see a little bit what's my timing. Okay, so the last piece that I would like to share with you is a reflection on methodology. So Armin told me that a lot of people might be interested in methodologies for quantification of metastability. I did a little bit of a review of the current state of the literature, and I did a little bit of thinking. So I'm going to return to this conundrum between transfer, which is a strong order in time, and synchronization, which is a strong order in space. And I'm going to remind you that we posit metastability in the dark area here, which is not completely synchronized and which is not completely serial or orderly in time, but which is both at the same time and not at the same time. And so because time and space commingle, we lack tools to analyze the organization of metastability. And I would like to say that the next 5, 10, 15 years, developing specific tools here is going to be a very important challenge to make progress in understanding flows in the brain. So I did a little inventory of what methods I could see in the current state of the literature. A lot of people have turned their attention to microstate, transient neural ensemble, board phase coherence, to try to quantify the serial aspect of mass action. So they started fixating the idea that there was a dynamic or a change, and then they looked within each window at the synchronization of the mass action that may happen. Some people have turned to quantify in models or in empirical data the number of energy level or the number of metastable states to try to appreciate this contribution of metastability to the complex repertoire of state that it gives to dynamic, the fact that the brain is not in jail or frozen, but can move very quickly through multiple spatiotemporal organization. Some people have looked at power law exponent or indications of spectral complexity. Other people have developed using graph theory measure or recurrent analysis the dynamics of functional connectivity, and I do believe that some of you are interested in that directions. Some people have used entropy measures at multiple spatial scales. A lot of people, especially in model, estimate the standard deviation of the order parameter, the collective variable, or some measures that are derived that go with the intermittency index. And a few people who have found very useful to move to perturbation studies of the brain have also studies of the relaxation of the change from one state to the other, using those index of perturbative integration latency. And then another aspect is to study turning curve when you manipulate the coupling. So my take-home message is going to be quite quick. I would like to tell you that metastability simultaneously enables information flow and mass action, even in reasonably endogenous conditions such as rest. So the brain is not frozen and waiting for something to stimulate it when it is at rest. It continues to have its lively life, and metastability accounts for that. It is driven by real-life complexity. Coupling is weak because each neuron, each neural ensemble is coupled to many, many different neurons and neural ensemble. It has a variety or a variability of intrinsic behavior, coupling and connectivity, which are full of asymmetries because of differentiation. It is adaptive because contrarily to your coffee machine or your car, parts, neurons or brain area, which has less than perfect match to one another, not perfect gears of a mechanical system, still retain the ability to work together for mass action. And the methodologies are a work in progress, and they face the conundrum that I described of spatiotemporal intricacies. And that's it for today.
Thank you very much. It was a very interesting talk. I really enjoyed that. So if anyone has a question, feel free to share in the Q&A, or if you want to ask it in person, I can unmute you. Just let me know. So I have one question for myself, and I can go through the question. So you mentioned the metastability doesn't indicate changes in the brain state, correct? Understood correctly?
There could be a higher order coordinative structure that creates this metastable regime, but is not fundamentally affected in rest. So the brain is an open system. We've been designing plenty of extremities, eyes, nose, ears, to gather information from the outside world, obviously. So each time you unroll this, you are in an open system, and those open systems can go through small change of the organization, which are inconsequential in its organization, or could go through those bifurcation, and the bifurcation is important. What I'm trying to say is that it seems reasonable at the current time to say that a metastable regime could persist for a long period of time. And even if you see in EEG those succession of states, they can be parts and parcel of a single regime, which spatiotemporally flows, and there does not need to be any change in the structure organizing the system.
So we have another question. Do you have access to the Q&A? If not, I can read it for you.
I probably prefer if you read it, because
Sure.
my layout make it a
Sure.
little bit
So
difficult.
the question is from Ashkan Faqiri. He's asking that I have a question regarding the definition of attractor and metastability and stability. I'm a little confused, as I thought attractors are a set of coordinates that the system moves around, evolve around, while metastability is a property of a system. But if I understood you correctly, you are treating these two terms as though they are opposite to each other. So
I would probably not go so far. I tried very carefully, but not carefully enough, to define the attractor or attracting tendency in the specific condition of this coordinative variable. So the coupling between the two oscillators. the metastable structure could itself be an attractor. That's not what I was trying to say. But the phenomenology that it drives for those 2 or 128 oscillators as attractor, when I can find fixed point in the graph of the rate of change of the relative phase as a function of its current state. And this is mathematically very well defined, difficult to find to determine in experiments. When we have metastability, there's no longer intersection between this ribbon and the plane phi dot equals 0. So it's meta, that means beyond, and stable point attractor, metastable. There's no longer stability of a coordination variable. So you see it dwelling, escaping forever. It's not trapped, it's released from the curse of eternity that I try to represent with this jailbrain. The jailbrain is a bad thing because if you want to move it to a different state, you need help from the outside world. You cannot be autonomous in your dynamics if you have states and attractors.
Feel free to ask your question on the chat or Q&A session. So I have one more question. Let's say someone wants to implement that in their study. Do you have like a toolbox or software that they can use, how they can study this metastability in their own data?
So I tried in one of the slides to do a little review of all the methods that I found in the recent literature. And I would recommend some of the toolbox which are listed in there. However, and if you put a message on the Slack, I can also try to see about. What I was saying in the very last slide, and I've been too fast, I apologize, is that those methods keep on going back to its propagation. And within the lens of propagation, I'm trying to try to understand the collective dynamics. So those, for instance, would be dynamic functional connectivity. It's synchronized for a period of time and then it's not. And this integration by part, synchronize there, synchronize there, synchronize there, one of the limits I see is that it does not capture the overarching organization, which transcends multiple of those small episodes and does not answer this important question I have, which is whether we are dealing with state transition, chimera, or metastability, because they look identical. And if they are different, way to treat disease, way to change the system is going to operate on very different principles. And we really want to know if it's one or the other.
Thank you. Since there's no question, I have more questions. Oh, there's a question, sorry. So Frank Hancock is asking, do the duals imply information flow? Like that was related to my question.
The dual is strongly associated to the collective behavior. It almost resembles the state of synchrony that you saw in the cat visual cortex for perceptual binding, but it is not destined to last because it does not have a state or an attractor linked to it. So at a time scale which depends on coupling strength, broken symmetry, the coupling between the parts is going to be released from it. Without energy or anything the system needs to do, it's going to disappear. The escape is related to the expression of the individuality returning to those functional units. So segregation or independence is in the escape, and collective mass action is in the dual, and therefore information flow are strongly driven by the escape dynamics. It leaves a chance for the system to reconfigure itself to something else.
So in the first slides at the end, you were trying to differentiate between information flow and synchrony, right? I would say one could argue that you can capture this information flow through the, for example, lag analysis to see how the different time points are synced to each other. And they are doing that, like when they are looking at the propagation, for example, and spatial dynamics do that. Would you mind to give some give some comment on that?
But I cannot give you a short answer to this. It's a very important question. In the ribbon model of this theoretical equation that I presented, you see the emergence of lagged synchrony that comes from broken symmetry. Neural ensemble at 7 Hz, neural ensemble at 8 Hz, they will synchronize, meaning their frequency will be the same, but because of their pull and push from their unequal intrinsic frequency, the attractor will not be 0 radiant, perfect in phase, or pi radiant, perfect anti-phase. It will be shifted a little bit to the right. This creates, and that's something we exploited to recognize real coordination from spurious coordination. This creates those ensembles which have a little time delays. This time delays does not reflect serial propagation of information whatsoever. It reflects the broken symmetry. And it has influence that I showed you a little bit later, that when they are phase dispersed, even if they are coordinated, they have a local function which is implemented, but this local function cannot be transferred to the higher up spatial level. That means that this information, it's like a gain control spatially, will stay local. This organization will stay local. But we cannot equate the phase lag in the neural ensemble with a definite evidence of propagation, because if it's a state of synchrony, the information is ubiquitous irrespective of the particular phase for this period of time.
Right. So Frank, follow up his question about dwell time. I'm also going to unmute him if he wants to ask himself more questions. So he's asking, during the dwell, if it is synchronization, then there could be communication through coherence. And I just want to mention, Fran, I unmute you if you want to continue follow up.
Okay, hi. First of all, it's female, but anyway.
Oh, I'm sorry.
No problem. I've just started a PhD, and the motivation for it was the metastable brain. So I'm in this pretty deeply. So what I'm trying to do is bring together synchronization and information propagation. And again, I've read all of the books and the papers. There's one where the information is created when there is a phase transition. That was from one of the earlier books from Kelso. I'm trying to figure out, again, in terms of the dwell, if the dwell is when various different elements are in some level of synchrony, then they are a possible route for information propagation.
I thought I would bore you to death with too many definitions, but one thing I should have done is a very clear distinction between three concepts: synchrony, which is the strongest part of coupling and coordination in an attractor; synchronization, which means a process to move from less coordination to more coordination, which is less well defined mathematically, but which is sometimes used to define synchrony and sometimes used to describe metastability, and metastability itself. Once this is done, your confusion might come from earlier work with Kelso and Bressler, where they equated metastability and relative coordination with those instantaneous state of synchrony. So this also comes with the work of communication through coherence with Pascal Frey, and this also relates to the past work of Bressler in coherence of a rabbit olfactory bulb with Walter Freeman. But those states of coherence are a tunnel vision of one period of the dynamics. And what I've been trying to do is to say that if we don't look at the whole dynamics, we might work on the wrong principle and focus on the wrong phenomenology, because we only capture a part and give it perhaps the wrong dynamical interpretation. So the dwell and escapes are intimately linked, and they cannot be dissociated for this reason.
Okay, thank you.
Thank you. So the next question, we can I'm pretty sure this one is a guy, because I can't recognize his name. Said Sani is asking if this is so, the Okay, sorry. So the question is, two oscillator with two different frequency, even if they are close together, can neither be synchronized nor show metastability. Is it correct?
Yes, that is absolutely correct. And it depends on two things. The thing that you already described, which is how far apart in frequency they are. It's easier for the oscillator at 7 and 8 Hertz to transcend their divide and bind together than the one at 7 and the one at 18 Hertz, obviously. And the second thing is the coupling strength. Both of those things interplay. So if they are very far apart and you pump up the coupling strength, eventually they will synchronize. It's a matter of putting more energy in the coupling strength. So in the mathematical model, we manipulate those two parameters, A and B, and we can put the very, very strong coupling that's equivalent to your mechanical system, your car, your gears. They cannot escape to one another when they are strongly coupled, right? And in the weak coupling, then the difference become a relevant variable, and they are always playing one with the other.
Okay, so he has a follow-up question. I'm going to unmute him if he wants to follow up. So he's saying, okay, so if this is true, which is true, what do you say about seizure, where the oscillation frequency gradually decreases?
What do I say about seizure, where
where the oscillations frequency gradually decreases? And unmute your side if you want to follow up later.
I would like you to go review the beautiful papers in 2004, 2005 by Perez Velasquez from Toronto. He has very beautiful thought about that. And there's an interplay of coupling strength and dynamics at multiple spatial scales, which is very obvious in seizure. People in Germany have also done very interesting work in the area since. What I would like to say is that the slowing down is always a sign that is very characteristic, I think, of epilepsy, of many more units recruited. If I return you to this Kuramoto and Batoktok chimera, the slowest mode of behavior is those 1/3 or 2/3 of the oscillation which are coupled. Couple is like a burden that you carry with you, which is going to prevent you to go fast. So something that is slower typically has more functional unit bounded together, and something which is faster, other things being equal, tend to reflect leaner, more independent dynamic of smaller clusters. So I think this might correlate to a counterpart to not too many things have been synchronized. They are slow, but they are going to eventually exhaust themselves.
Thank you very much, Emmanuel. Thanks a lot. Yeah, thank you.
Thank you.